The broadcast is now starting. All attendees are in listen-only mode.
Hello, good afternoon, everyone. My name is Anna Zylik, and I am with ICF. We are the vendor working on behalf of the sponsors of Energize Connecticut to bring these passive house trainings to all of you. So thanks for joining us today. We will be recording this training and we will make this available afterwards to you all. These trainings are at no cost thanks to the sponsors of Energize Connecticut and are a part of a partnership with Connecticut Passive House. A quick reminder that as part of this training and workforce development initiative, we are offering a 50% cost reimbursement for individuals pursuing either FIAS or FEE professional accreditation. So this includes the cost of the training and the exam, and once you become certified, we'll work with you to process the 50% cost reimbursement. So if you have any questions about that, please don't hesitate to contact us. And with that, I will pass it over to Keegan, who's also with ICF, to talk about the passive house building incentives.
Thanks, Anna, and hi, everyone. Thanks for joining us today. In addition to this no-cost educational training series and the professional accreditation reimbursements, the sponsors of Energize Connecticut also offer incentives for builders and developers who choose to pursue passive house certification in multifamily residential projects of 5 units or more. Next slide, Adam. The passive house incentive design for Energize Connecticut is shown here on the slide and includes pre-construction incentives for things like feasibility studies and energy modeling, and post-construction incentives for full passive house certification through either FIAS or PHI. Our goal is for everyone involved in multifamily construction, residential construction in the state of Connecticut to be aware and understand these incentives. So if you're interested in learning more, please do visit the website or contact us at the information here on the slide. And for questions during today's session, use the chat function throughout, and Anna and I will relay them to Adam as we go. And with that, I will turn it over to today's presenter, Adam.
Great. Thank you very much, Keegan. So today we are going to be talking about heat pump design and installation best practices. My name is Adam Romano. I am a principal building systems consultant with Stephen Winter Associates. My contact information is up here on the screen. If any questions happen to come up after the presentation, you want to reach out, or you have a project you're working on and need a little assistance, please always feel free to reach out to me. A little bit about Stephen Winter Associates. We are a consulting firm that provides energy conservation and management services, sustainability consulting, green building certification, accessibility consulting. We do a lot of research and development and a lot of workforce development as well. Our information is up here on the screen. swinter.com is our website. So with that, there's been a lot of talk, and a lot of you, I think, have been in this movement, and a lot of talk about electrification in the last few years. And there's been a few drivers that really have pushed the need to find electric-based solutions to the forefront. And mainly that is looking at ways to reduce carbon emissions locally in our building stock. There's other benefits as well besides the carbon emissions reductions. I mean, obviously we have improved local air quality from not burning fossil fuels locally in our homes. That translates into improved indoor air quality. There's a reduced risk of carbon monoxide exposure because, again, we're not burning those fossil fuels. There's comfort benefits as well to moving towards electric-based systems, especially when we look at some of the systems that can provide more of a zoned approach to design. And then in certain parts of the world, there is cost savings as well, depending on the cost for fuels and how that balances out. So there's been a lot of movement and momentum towards electric-based solutions. And you see, it's these electric-based systems applicable to a lot of different construction types. Obviously, new single-family homes is one that is a great spot for electric-based systems because we have much more control over the loads. We're doing a good job of air sealing, insulation, a lot of the detailing on our enclosures that helps make the loads a lot lower and makes these systems a lot more applicable. So you see that we can do a real good job designing and installing these systems to really optimize performance in new single-family homes. They're also, applicable to existing homes as well. We see a lot of retrofits taking place all across the country, and here, a lot of it is driven by paybacks and return on investment when we're looking at, switching from delivered fuels to electric-based heat pumps, and we also see a lot of beneficial cooling being added as well in projects that don't have a dedicated central cooling system. So there's a lot of momentum in the existing single-family market as well. And in the multifamily market, obviously, heat pumps can work well in different building typologies, and multifamily is one of those as well. So we see a lot of heat pumps being installed in high-performance projects, and they perform very, very well when we have equipment that is selected correctly. That's where we see a lot of good performance, and that's kind of what we're going to be talking about today. Is really making sure that these systems are designed, selected, and installed correctly in order for us to ensure that performance. Sometimes, we see performance gaps or issues that come up post-installation, and a lot of it stems back to those variables. So today we're going to talk through a few different things during this webinar. We're going to understand how these heat pumps work and their applications. We're going to determine the most appropriate system configuration for different types. We're going to recognize the signs of a quality installation, and we're going to talk about some of the commissioning of new installations as they get started up. So with that, let's jump into system design. Here we're going to be talking about sizing and selection. So when it comes to sizing, selecting these types of systems, the first thing we need to understand is the requirements. So we need to make sure that we are going to correctly size these heat pumps and select them correctly, because that really ties into the efficiency and the performance. If the capacity is too low, the system is going to go into defrost mode during the heating cycle. It's going to not be able to meet the load, which is going to cause inefficiencies and performance problems. If the capacity is too high, we may have excessive cycling and poor performance at warmer temperatures that can pose an issue as well. So we really need to gather all the information that is needed to really understand what's going to be the most appropriate system type for our particular project. And a lot of that goes back to the goals, things that we're trying to accomplish with installing any type of HVAC system. We're really trying to maintain comfort. We want to make sure that the system is going to work economically. We're going to have, a proper cost in terms of the operational cost. And we want to make sure that, we're paying attention to how the system is installed so that we don't have any sort of environmental impacts from things like refrigeration leaks and the like. So we really want to make sure that we're, always going back to those goals and making sure that we're trying to achieve them as we start to go through this entire process. And a lot of, sort of the selection is also going to depend on the layout of the particular home or the particular project that we're working on. Is, the space more of an open floor plan? If the space is open like that, then that may lend itself to more of a ductless option. If the space is much more compartmentalized, we may work towards more of a ducted solution, right? We want to be able to make sure that we're selecting this equipment and it's going to work well in with the configuration of our particular space. So that's one of the main drivers, is kind of how the space is laid out can kind of dictate the options that we would go for when we're looking at selecting terminal units in the interior. And then also, like I said, proper sizing is going to be important as well. It's sort of it's like a sort of a Goldilocks issue, right? The idea is we want to make sure that we're not installing something that's too small or too big. It needs to be just right. And if the system is too small, we're not going to be able to perform. We're not going to be able to heat the home adequately, heat the space adequately, or cool the space adequately during those parts of the season. So we're going to have poor, comfort as a result. If we are looking at this as a retrofit scenario and we're keeping some existing systems in place, we may rely more on backup or auxiliary heating or auxiliary systems to be able to meet that load or meet the balance of that. We may also have issues with catching up after setbacks. If we are utilizing, let's say programmable thermostats, we're performing a setback during unoccupied times, it may take a lot longer for that system to recover when the space becomes occupied. So all those things, really, are a result of a system becoming or being sized too small. Now, too big is an issue as well. Here, we're going to have poor comfort because we're going to be overheating spaces or overcooling spaces or not dehumidifying the space. We're going to have poor energy efficiency as a result because the system is going to cycle because it's not going to be able to, it's going to be too big for the application. We can have poor durability, right? As we're cycling the system more and more and more, we also have issues with, stressing out components more and more. So we may not, see the expected sort of useful life out of this equipment over the time because it may be cycling more frequently than it was initially intended. And it'll be more expensive. The operational costs will be higher because our capacity is too big. The first cost will be higher because the equipment was installed it was too large. So all of these things, sort of come into play when we have a system that's too large. So we really want something that's just right, and that's going to provide us with, our goals: the comfort, efficiency, and durability. Now, during this training, we're not going to get into all of the sizing aspects, but we will point you in the right direction in terms of resources that are out there. So, we're not going to go through, manual J, manual D, manual T, manual S, and how to, design and perform a heat loss calculation and design ductwork and things like that. Those manuals are readily available. There's training on that. There also are guides that we are going to point you to in terms of sizing and selecting air source heat pumps in cold climates. So NEEP, the Northeast Energy Efficiency Partnership, there's 2 links here to a guide for sizing and selecting and a guide for installing these heat pumps in cold climates. And those are great resources that will complement this training and will, sort of help you, navigate some of the your projects as you start to go along. Now, once we have the system sized, right? So the idea first is to make sure that we have a system, again, it's not too small, it's not too big, it's just the right size. Now we need to sort of select the system type, what kind of heat pump are we going to install? So we have a couple of options, when it comes to system configuration. So one of the things that you can, opt for, and we see this a lot in projects, is going for smaller units and having smaller mini splits, taking care of parts of the load throughout, a building. So we can have these smaller sort of decentralized air source heat pump systems, and these are typically, 1.5 ton, 2 ton, 3 ton systems that can go ahead and, carve out, and take care of a piece of the load. These systems, again, have 1 indoor unit, 1 outdoor unit, so they're this 1-to-1 configuration. The indoor units can be a lot of different types. You can have a low wall or a floor mounted unit, as you see here. You can have your traditional, high wall ductless unit. You can have ceiling cassettes. You can have ducted units that are compact ducted. So you have a lot of options in terms of the terminal unit that's going to fit your space best. And again, going back to, is the space more compartmentalized or is the space, more of an open concept? We can, determine whether we're going to go with a ducted or a ductless approach in that case. If we want to combine, some more spaces together, for one larger system. So if we have areas that are going to, sort of have the same kind of, cooling and heating load, and we want to go ahead and combine them into one larger system, we may move up to sort of a multi-split. Where here now we have multiple indoor units that are now tied to 1 outdoor unit. And then here, we have refrigerant piping that's going to go to these indoor units. And again, we have the same sort of flexibility when it comes to the terminal units, whether they're going to be, floor mounted or high wall or compact ducted. We have some flexibility there within the manufacturer's requirements or, capabilities. And then here again, it's 1 outdoor unit, multiple indoor units, a little bit larger in size. Here you're going up to your 4 ton, your 5 ton systems. So again, you have a little bit of a larger system. Now, one of the things we will, sort of caution with this approach, and this is, very, sort of relevant for passive house projects where we have very low internal loads, is that sometimes we see performance issues with these multi-split systems. And the performance issues come in play because of those lower loads. Now, these units can modulate down, right? That is one thing that makes these units very, very attractive, is that they have the ability to ramp up, ramp down, they can modulate their capacity. But there is going to be, sort of a minimum capacity that they can't really go down below, right? Especially when you have a lot of connected terminal units in the building. So there's going to be a minimum capacity that, that's as far down as we can go when we come to ramping down. Now, if that minimum capacity is greater than your load, then you may have issues with cycling. And that ends up causing the units to be less efficient over time. And because essentially those terminal units are oversized for that particular space, right? So if let's say an example of a 3-bedroom, home, if we put one ductless unit in each one of those bedrooms and connect it to a multi-split unit outside, chances are in certain periods of time that those units are not going to be able to modulate down to meet that load, especially in an efficient building. And that is, one thing that, we do see a lot. And manufacturers now are starting to recognize that and see that as, projects are being, commissioned and getting into operation, that you will have some issues if those units are larger than your load. Right, and you can have things like overheating, obviously, because now we have to shed the BTUs, we have to get them out into the space. Overheating can be an issue. During the cooling months, humidity can be an issue, right? Because we're doing a lot of sensible cooling at that point. We're bringing the temperature down, but we're not doing any latent cooling. We're not doing any dehumidification because the units are larger than the load in the space. And we can also have higher than expected energy use, right? Because now, again, the unit is bigger than what we need. So all these things go into that. So when you have these, high performance buildings with these very low internal loads, what we like to do, we like to see you combine more of those spaces and then go opt for more of a ducted solution at that point instead of going with ductless, because now we can combine those spaces. We can have one internal unit and that the load can be higher than its minimum turn down. So that's something that, we like to see. Or you split it up and you say, okay, well, we're going to now put 3 one-to-one units that are going to serve that space instead of one big unit that's going to serve multiple spaces. So there's ways around that, but that's one thing that I would caution and just make sure of, is that you're looking at all the performance data to ensure that the system is going to be able to modulate down to your expected loads. And then the other option besides sort of the multi-split and the mini-split, we have traditional sort of central split systems where, we may want to go and fabricate a ductwork system, all right, and have a traditional sort of air handler connected to an outdoor unit. And then that's going to serve the space through, traditional ductwork system. Here, this is, very reminiscent to the more conventional AC systems. They're typically come in the 2 to 5 ton range. Again, they're going to be fully ducted. And here, sort of the approach is to really make sure that the ductwork construction is done very, very well. One of the things that we find with heat pump systems is that the discharge temperature is not as hot as you would find with a traditional fossil fuel-based system. So if we are burning oil or we're burning propane or natural gas, discharge temperatures can be, above 130, 140 degrees. Whereas, with a heat pump, we're typically around 110, 120 degrees. So all the heat that we are generating, even though it is enough to be able to heat the space, we need to make sure we're not losing any of that heat along the way. So we want to make sure that the ductwork is insulated, it's air sealed, so that all that air can get to the spaces it needs to get to in order to properly condition them. We also want to pay attention to the size of the ductwork, because we want to make sure that we maintain proper velocity as the air gets distributed down the line. So all the good sort of ductwork practices listed out in Manual D, we want to make sure that we're following when we have these ducted systems. And that's, any ducted system, whether it's compact or if it's, sort of centrally ducted like this. Now, when it comes to, selecting, once we figure out sort of the type that we're going to use, right? So whether it's a central system or a split system, what are we going to, sort of select? Now it comes into, okay, well, what type of manufacturer and, what type of unit we're going to put into this project. And here I'm going to go back to that neep.org and look at their database. Now, One of the things that you see when you look at conventional heat pumps is that the way that the capacity is reported traditionally, leaves, sort of some questions, right? So when you look at traditional heat pump performance, they're typically rated at 47 degrees Fahrenheit and 17 degrees Fahrenheit. And, that's fine if, one of those happens to be your design temperature. But if your design temperature is, below, 17 degrees, then, sort of what do you do? Because you need to make sure that your system is going to be able to heat the building at the coldest expected temperature. And, the relationship between that 47 and 17, may not be linear, right? You may not be able to extrapolate that out and say, okay, at, 15 degrees, 12 degrees, 10 degrees, we're going to see this, because the drop off may be more severe. It may not be a linear relationship between capacity and temperature. So we really need to get into more of the engineering data to see, okay, well, how do these systems operate down at my expected, outdoor design temperature? And that's what, one thing that, this database has done is really allow you to compare systems and really get that data and much, much more easily instead of running through engineering manuals to try to find that data. So here you can see one example unit. This is a 18,000 BTU split system that is non-ducted. And we can see on the right-hand side, we have all these detailed performance specs, right? We have the cooling capacity up to 95 degrees. We have heating capacity all the way down to 5 degrees. And what they're showing here is the minimum capacity as well as the maximum capacity, and then also the efficiency. So the coefficient of performance, how efficient can we move this heat at those particular temperatures. So this makes it a lot easier to ensure that, our systems are going to be able to move the right amount of heat or the amount of heat that's needed for our lower ambient temperatures, or down to 5 degrees in this case. So if that was our outdoor design, this unit can provide 15,400 BTUs at 5 degrees, and that we want to make sure that's adequate for our space. So this is great to sort of reference, and every manufacturer is going to be a little bit different, right? So some units are going to be kind of engineered differently, and that's something that you also have to pay attention to. You can't just say that, oh, one 18,000 BTU unit is going to be the same as another unit, because they may be slightly different in terms of how they're designed and how they're engineered. So we have a little example here in terms of comparing two units that are on the list that meet the specification. These are both 1-ton ductless heat pumps. We have heat pump A and B, and we're going to look at sort of the capacity and the efficiency at different outdoor temperatures. So we can see here that heat pump A, in this case at 47 degrees outside temperature, can produce 18,000 BTUs an hour, can move 18,000 BTUs per hour, which is greater than its nominal capacity of 12,000 BTUs, because it's a 1-ton ductless heat pump. Heat pump B can move even more heat. It can move 21,000 BTUs per hour. But you can see the efficiencies are a little bit different. So for heat pump A, the coefficient of performance is 4.15. So it's producing a little bit less heat, but it's doing it in a much more efficient way. Whereas, heat pump B is down to 2.68. So it's providing more capacity, but it's doing it in a little bit of a less efficient way. And that's going to be important because, again, these two are not going to be equal. As we get into different outdoor temperatures, here we're down to 5 degrees, and we can see now the difference starts to get even greater, right? Heat pump A now can only produce about 8,000 BTUs, whereas heat pump B can produce about 13,000 BTUs. And the efficiencies, you can see 2.81 for A and 2.21 for B. So you can see that, heat pump A is being designed more for, efficient operation at higher ambient, whereas heat pump B is being designed for more capacity at lower ambient temperatures. And it even becomes more clear as we get to even colder and colder outdoor temperatures. Here we're down to -13. Heat pump A doesn't even show any data for that particular outdoor temperature, whereas heat pump B can still produce about 9,000 or almost 10,000 BTUs with a COP of 1.81. So again, from the outside, just looking at these units without peering into all the detailed sort of engineering specs, you would think, okay, the performance should be pretty much the same. Whereas, but if you really peel the onion back a little bit, you can see that systems are definitely different. And that's something that, this, sort of specification in this database really helps to illuminate is, what system is going to provide me the most output or the output that I need with, the greatest efficiency. And, that's kind of, the example here is you really need to compare different types of systems for your application because they're not all going to be the same. So once that is all done, once we say, okay, we've sized the system, it's the right size, we selected the right configuration, we made sure that it's going to provide, capacity in an efficient way. Now we need to get to the part of installing it, right? Because that's the second, a biggest issue when it comes to heat pump performance is, proper installation really does matter in terms of how these systems get installed and their long-term performance and capabilities. So let's shift a little bit and talk about some of these installation considerations. Now we're going to break it up and we're going to talk a little bit about indoor units and then outdoor units. So on the indoor unit, placement is going to be important, right? Just because we selected the system correctly and we sized it correctly, we still need to make sure that it's installed and it's placed in the interior in an efficient way. So we want to make sure that it can broadcast air into the space so we can adequately sort of heat or cool that space. We also want to make sure we have enough clearances for service. Having a unit that's 15 feet up in the air is going to be very, very hard for the end user to change those filters, and those filters may not get changed more frequently enough. That may cause performance issues. So all of this has to be taken into account when we're deciding on where we're going to place this indoor unit. We also need to make sure that we have proper clearances from the ceiling so that we have adequate airflow into the return side of the unit. And we also want to make sure that, again, the unit is available for service. If you need to open up the side panel, we want to have clearances to the left and to the right to be able to service that unit if it needs a motor replacement or if it needs, more invasive, service. Now, high wall units like this, there are some issues with placing them very high in heating dominated climates. And one of the things that we do see, and if you look at some of the data from manufacturers, is that as you start to place these units higher and higher on the wall or higher and higher in the space, they tend to work a little bit less efficient during the heating months. And that has to do with, sort of the properties of air. As you heat air up, it's going to become lighter. It's going to rise to the top of the space. So we're going to tend to have higher air temperatures at the ceiling level compared to the floor level. And as you have these elevated temperatures up at the ceiling, that correlates right where the return air duct is for that particular unit. So it's pulling on a ductless unit, you're pulling air in from the top and you're discharging it through the front. Now, if you're pulling this really hot air, relatively hot air from the ceiling into the return, it's going to be much harder for that unit to sort of impart the BTUs, to be able to transfer the BTUs from the coil to the airstream. Because as the delta T gets smaller, it becomes harder and harder for that system to move the BTUs to that air. And that's what you see here on this diagram here on this chart. You can see as the return air temperature goes from 65 to 75, you see that your capacity drops because, again, we're not moving the BTUs effectively, and our efficiency drops because now we're returning more BTUs to the outdoors. So when you're looking at placement of this indoor unit and you're in a heating dominated climate, and you're going to spend a lot of time in a heating mode, it may be better to move towards a floor mounted unit. It may be better to move towards a compact ducted unit where we can sort of control where the return air comes from to kind of alleviate these issues, because we have seen performance problems or performance degradation when you have these units up really high and they're pulling in a lot of that hot return air. When it also comes to indoor units like this, when they're ductless, I like to see a overflow or a wet switch installed as well, because these are in the interior space, and they're there. If we have any condensate blockage in the condensate lines, or if we have a blockage in the condensate tray, we don't want condensate to spill out and damage interior finishes. So having a wet switch there, an overflow switch there, is cheap insurance to prevent that from happening, because it'll de-energize the unit during the cooling season, prevent that pan from overflowing, and and save a lot of the interior finishes. So that's something that I always like to see on indoor units in ductless in the ductless unit, is to make sure that we have this form of a disconnect if we had a blockage, especially if maintenance is not being done correctly. If filters are clogged, you tend to have more debris getting into those condensate pans. Now, outdoor units are also important in terms of the placement. So, you want to make sure, again, we have adequate airflow going through these units. If you look at these units in particular, a lot of the coil surface area is behind the unit. So we need adequate, sort of offset from the structure. So we want to make sure that we're maintaining, manufacturers' clearances, 12 inches, 8 inches, whatever it may be from those manufacturers. You want to make sure that we have adequate clearance from the behind and from the side. This way we can have good airflow going through those coils. We also want to make sure that they can be serviced, right? So you want to make sure they're in a spot where it's easy to be able to service those units, clean off the coils, check all the electrical connections. That's going to be an important aspect as well. These brackets that you see here are very common. A lot of folks like to get them up off of the ground. So one thing we need to make sure of when those brackets are installed is that they are anchored very well into structure. A lot of these units, especially when you get into the multi-splits that are higher capacity, you see a lot of these units weighing 300 pounds, 400 pounds. So we need a bracket that can support that kind of weight. And we need to make sure that it is, secured, into that structure so that we can have a good sound installation there. These units also, we would like to see some sort of vibration isolation from the unit to the bracket itself. Even though the units are very quiet and they ramp up, with these variable speed compressors, we're not, hard starting them. They're going on very gradually. They ramp up, very slowly. But the issue still happens when you have, very cold temperatures and those compressors are moving at very high RPMs. There may be some, vibration that gets transferred into the structure. So we do want to see vibration isolation on those legs, and then also proper fasteners to be able to secure that unit to the bracket. That's going to be very, very important as well. If you choose to install these units on a pad, that's the other option instead of using a wall bracket. Here you want to make sure that the pad is level. We see this a lot, especially level over time, right? It tends when these systems are installed on these fiberglass pads or concrete pads, sometimes they tend to settle. And then you go back 2-3 years later and you see that the unit is not level anymore, and that can have an impact on lubrication at the compressor. So here you want to sort of dig down and make sure that you can pack the soil, or use some sort of stone dust or drainage stone to be able to make sure that we have a good level surface that's going to stay level for long periods of time. And then here you may have to install feet to get these units up off the ground, because we do need to pay attention, and we'll talk about this later, to snow clearances, right? So we have an anticipated snowfall amount. We need to get the units up off the ground so that they can drain properly during defrost, and they're not impacted by, the snow surrounding them. Sometimes you see outdoor units stacked. So in certain situations, outdoor real estate becomes very hard to find. And you may, want to sort of stack these units where you have one unit installed above another. The one issue that we see with this, and this happens frequently, is that during the heating months, these units may go into defrost at different times. And if the unit above goes into defrost while the unit below is still in heating mode, any of the runoff that is produced during the defrost cycle is going to drip down onto that unit below. And if that unit below is in heating mode, those coils are going to be very cold, and that runoff may start to refreeze on that bottom unit. So here, if we are going to stack units, we like to see that there's some sort of, piping or some sort of way to divert that runoff so that it doesn't go onto the bottom unit. Because as it goes into the bottom unit, it's going to go into defrost cycle more often. It's going to reduce its capacity because it's going to be harder to move air through, a frozen coil. And that's going to cause performance issues with that bottom unit. So we need some way to kind of divert that away so that it is not impacting that bottom unit. Now, runoff from defrost is not the only thing that we're worried about when it comes to these units in heating operation. Sometimes you may have, parts of the roof line that do not have gutters and leaders, and water during rain events may go down and fall on top of these outdoor units as they are in heating mode, and that may cause them to freeze up. So we also want to pay attention to that. Where are these units being placed with respect to different roof lines? And if it has to go in this one location, we have some sort of fabricated option, like you can see on the right here, that is going to kind of catch that water and divert it away from the unit. So it's not going to impact its performance. Because the same thing is going to happen here. We're going to have that water run off. It's going to freeze on the outdoor unit, and it's going to impact airflow, and it's going to impact system performance. So that's something that we want to pay attention to as well when we're siting that outdoor unit. As I mentioned before, snow is a design consideration, right? And in our area, we are going to get snow. Typical snow depths are going to vary depending on where you are. But that's something that we have to pay attention to, is making sure that the unit is up high enough that it is not going to be impacted by a snowfall event. The unit is not going to be installed, let's say, in an inside corner of a home where you can have snow drifts several feet high that can impact the performance of the unit. And also just education for the end users. You may have to go out there and clean the units off, make a path, remove some of the snow that's surrounding those units during the winter, because you want to make sure you're maintaining those proper clearances, especially if this is your sole source of heat. We need to make sure we're getting good airflow through the unit, even if it is snowing outside. Once you select the location for the indoor and the outdoor unit, the next process is now routing the refrigerant line set. So we need to be able to get the connection made from the indoor unit to the outdoor unit. So here, when it comes to best practices for line set installation, we would like to see the use of a tubing bender being employed. Because again, this is ACR tubing. We can go ahead and bend this tubing as opposed to using joints. And we're really trying to here limit the amount of joints that we have to field fabricate and limit the potential for refrigerant leaks. So because this tubing can be bent fairly easily, you can use a variety of tubing benders to go ahead and manipulate that piping so that you can route around objects and get from point A to point B. So that is something that we like to see used a lot when it comes to our line set routing and installation. Now, there's going to be times where it's inevitable and you have to go ahead and fabricate a joint in the field. So here, when we are making, joints in the field, we do want to make sure that we are following proper brazing techniques so that those joints are brazed. So we're using acetylene and we're using a brazing rod. And we want to make sure that the filler material completely fills the joint itself. We want to make sure that we're properly heating both ends of that copper pipe so that we have good flow of the filler material inside of that 90 in this case. And we also want to make sure that we are purging nitrogen through the line set as we are brazing the pipes together. And that what happens here, if we don't purge nitrogen and remove the oxygen inside of this pipe, as you heat that pipe, with that acetylene torch, you are going to have an interaction between the copper and oxygen, and copper oxide is going to form. And that's what you can see on the bottom here, is that all this black copper oxide has formed inside of the pipe. Now that becomes an issue as that flakes off, as the refrigerant is allowed to go into the line set, it's going to go ahead and interact with that copper oxide. Flakes of that copper oxide are going to break off, and they can pose an issue to devices that are downstream, such as your electronic expansion valves that are very, very small openings. They're metering the refrigerant into the, into the coil. And if one of those little flakes of copper oxide gets caught in there, that can cause, an issue with operation. So we want to make sure that as the brazing is happening, that nitrogen is being purged through, and they make regulators like you can see on the bottom left here that have braze settings. So they'll just purge a little bit of nitrogen through, displace that oxygen while the brazing process takes place. And you can see the joint on the top had nitrogen going through, and that is now nice and clean on the inside. So this is going to be very important for when you have to make joints between the indoor and the outdoor units. Now, the other method of joining piping together, and you see this at the terminal units, at the outdoor and at the indoor unit, is the process of making a flare. So this is more of a mechanical connection between the copper piping and the brass coupling. So here you want to make sure that you're using a good flaring tool. The flare is a uniform, so you're kind of splaying out the copper. Usually it's about a 45-degree angle. You want to make sure that it's uniform all the way around. It's the proper depth. It's not, misshapen. And then when the flare nut is, attached to the unit, you want to make sure that you're not using too much force. So most manufacturers will recommend using a torque wrench and making sure that it's snug, but it's not too tight. When you tighten up that flare nut too much, it puts a lot of stress on the backside of that flare. And because, again, this is ACR tubing, it's pliable, you can start to see that flare, get flattened. And in extreme cases, the copper can crack, and that'll cause a refrigerant leak. So we want to make sure that, the flares are made correctly, and we're not over tightening that flare nut when we, land that line set to the indoor unit or to the outdoor unit. And now once we made our connection, so our connection's now made between the indoor unit and the outdoor unit, now we need to make sure that we don't have any leaks. So the next process is to pressure test these units, pressure test our line set. This way we have, confirmation that we do not have a refrigerant leak. So here you're going to pressurize it with dry nitrogen. Typically over 500 psi is recommended by most manufacturers. Some manufacturers would like to see a standing test for 24 hours, and then you would go back and reevaluate to see what kind of pressure you have after that period. Some are shorter. So you want to go in and just follow the manufacturer's recommendations to ensure that we have, proper joints that are made and that we don't have any leaks between those two units. Because again, the big thing with this is that, we don't want the refrigerant to leak out. It's, a performance issue, and it's a big performance issue, a comfort issue, but it's also a big environmental issue, right? We don't want that, that refrigerant leaking out into the atmosphere because of the effects it has when it's leaked out. Its global warming potential is very, very high, typically with 410A and other refrigerants. So this is going to be a very important part of the installation process, is really making sure that we don't have any leaks on the joints that we've created in the field. Once the everything is made up and we feel confident that we are leak-free, now we have to sort of reinstall some of the line set insulation. Because again, as we're brazing or if we're making a flare, typically we remove a section of the insulation, and now we need to sort of reinstall that. So we want to make sure that our insulation on the line sets is continuous. It is, goes from end to end. We don't have any gaps. It's properly secured. We like to see the use of a line set insulation that has an integrated UV barrier, because as the line set exits the home or exits the structure and connects to the outdoor unit, if it's exposed to ultraviolet light from the sun, you usually see degradation of that insulation. And there's plenty of examples. If you go back, 2-3 years after an install, you see that the insulation is falling apart and it's coming off of the piping, and that's due to the UV exposure. So we want to see one that has, an integrated UV barrier, or we want to see a UV wrap installed around the line set to make sure that we're protecting it from that degradation. Then we also need to detail the exit point. So as the line set is going out of the structure, we want to make sure that it is properly sealed. Now, folks in the passive house community, you're going to use a lot more robust connections there to make sure that we have a good air seal. We're maintaining air barrier continuity, but you want to make sure that that does take place, that we have a good detail for those pipes, especially if we have multiple units. We're going to have a lot of penetrations through our air barrier, so we want to make sure that we're properly detailing all of those pipes as they exit and they go towards the outdoor unit. You can also dress up the line sets on the outside. There's a variety of products that can be installed, line hide, things like that, where you can cover the line sets so they kind of blend in with the exterior of the building. Once that is all set up, then we can evacuate. So the line sets, before we can introduce refrigerant into our system, we need to remove all of the air and any of the non-condensables that are present inside of the copper piping that we've just installed. So we're going to use a vacuum pump here to remove all of that. We want to get down to at least 500 microns, if not better. If you're finding it hard to get down to 500 microns, there may be a couple of things. You may have moisture in the system, especially if the installation happened over a period of multiple days, and maybe it did rain and the line set wasn't capped off during that period. You may have good excess moisture inside of the line set, and that may take a triple evacuation process or multiple vacuums to really pull all of that moisture out. It may be due to a vacuum pump oil being old. So you do need to maintain the oil in your vacuum pumps. If the oil does get old, then it becomes very hard for that vacuum pump to get down to those levels. Or you may have a leak, right? So then you may have to go and reinvestigate your joints and make sure that we don't have a leak. Because if we can't get down to the 500 microns, it may be that air is coming in at some point through a very small leak on one of the joints or one of the flares. Once we achieve that point, then we want to go ahead and charge if we need to charge. So, depending on how long the line set is between the indoor unit and the outdoor unit, we may have to add additional refrigerant to make sure that our refrigerant charge is adequate. So that's something that we're going to do with a digital scale. We're going to ensure that we are following the manufacturer's guidelines into how many ounces need to be installed, per, excess footage. And then make sure that we're precisely metering that into the system before we go ahead and release the refrigerant charge. Once that's all set up, the refrigerant portion of the installation is complete. We can go ahead and back off the valves and close everything up. And we can turn our attention to making sure that the system is powered correctly. So on the wiring side, we have to bring power to these units. So we want to make sure that the overcurrent protection is sized correctly. So as we go from the panel to the unit, we have a circuit breaker in place. So we want to make sure that that overcurrent protection device is sized, based on the nameplate rating of our unit. We want to make sure it's properly labeled so that we know that it is for our heat pump system. And we also want to make sure that our conductors are sized correctly, that we have the right wire gauge, the right insulation type, and that our conductors are compatible with the terminals on the overcurrent protection device, the disconnect, and our unit itself. So all that needs to be done to make sure that we have a safe installation. At the disconnect, typically we're going to have some means of disconnection between the power coming from the panel and the outdoor unit. That disconnect needs to be sized correctly for the ampacity of our outdoor unit. Sometimes some jurisdictions will require a fuse to disconnect, like you see here. Those fuses then also need to be sized based on the nameplate rating of the unit itself. That disconnect should be in a place where it's easy to reach. So in case of an emergency while the unit's being serviced, we can de-energize it, or we can make sure that it's not re-energized as we have a service tech working on that. Interior wiring needs to be landed correctly. The biggest issue we see with this is just mistakes when it comes to which wire is going to which terminal. A lot of these units either have A, B, C, or 1, 2, 3, making the connection between the outdoor unit and the indoor unit. So we really want to make sure that we're following that color coding correctly, and that both the indoor unit and the outdoor unit have a proper ground. So making sure that they're grounded to a designated grounding lug is going to be important for operation. right? And again, just making sure that the communication and power cables, are the same color or the same ones as we go between indoor and outdoor units. Sometimes that gets a little bit messed up. Some jurisdictions will require a means of disconnect at the indoor unit as well. So you see this is a 3-pole disconnect switch that can be used for service or repair. So for instance, let's say you have a multi-split unit and you have multiple indoor units and one outdoor unit, and one unit it needs to be serviced. Of the indoors, you could just turn the switch there, keep the other units operating, and then it's safe to work locally on the unit that has the issue. So again, some jurisdictions require that. It is a good practice to have a means of disconnect on the inside. This way you can get properly service and safely service that indoor unit. And then the last thing is controls. So here we always advocate for wall-mounted thermostats as opposed to handheld remotes. Just because when you're utilizing a handheld remote for a ductless unit, the return is the space temperature is being sensed at the return portion of that unit, so it may not be accurately representing what the space temperature is because, again, of the warm air rising to the top. So we would like to see wall-mounted controls that get a better representation of what the indoor temperature is. This way we can really make sure we're driving comfort. And you may have to, we also like to see integrated controls as well if you are using 2 different types of systems. So we want to make sure we prioritizing the use of the heat pump, and then we have our auxiliary coming in when needed. And the last thing is going to be startup. So once everything is started up, we want to verify we have proper voltage at the indoor and outdoor units. We want to make sure we perform a heating and cooling check to make sure that we have proper operation there. Record system supply and return temperatures to make sure that those temperature splits look good. Test the condensate drains. These are all good things that we should be doing during the startup process. So with that, I do want to summarize what we talked about today and open it up for questions. The biggest thing with heat pumps is reducing the building loads helps reduce the size of the heat pump. It'll improve the cost effectiveness, the performance, the capacity. We want to make sure that we route our refrigerant lines in the most direct path possible. Make sure they're protected from damage. Make sure we have as little joints as possible. We want to make sure we locate all of our units correctly, both indoor and outdoor. And then also just stay up to date with new alternatives, right? There's a lot of innovation happening in this industry. So as we start to get new systems, out into the market, keep up with that, look at that performance data, and make sure that we're selecting the right product for our particular project. So with that, let's open it up to questions if there are any.
Hey, Adam. Yeah, there's a couple questions. Can you hear me all right?
Yes, I can hear you.
All right. Can you just speak a little bit about how heat pumps work with existing ductwork? So taking existing ductwork in a house and adding a heat pump.
Yeah, so one of the things you have to pay attention to, and I kind of alluded to it in the beginning when we were talking about central systems, is that when you look at a heat pump system, those ducts were sized for the flow rate and the discharge temperature that we are going to see on a conventional furnace or a conventional, typically just conventional furnace or conventional air handler. So when we install, these heat pumps, we have to pay attention to our external static pressure, how much pressure they can produce, those fan motors, and then also our discharge temperature. We, most of the time when you're doing this, you may have to modify the ductwork to ensure that we can provide the right amount of flow, because the external static pressure may not match up with what was in there previously. The temperatures obviously are going to be lower, the discharge temperatures. So we need to make sure we insulate, we seal that ductwork. But a lot of times it is going to require some sort of ductwork modification, either on the supply side to make sure that we have good velocity to all the end spaces, or on the return side to make sure we have adequate return coming back from the space to ensure that we don't have really high pressure across the unit. But a lot of times, ductwork is an issue, and even in just conventional system installation. So most of the time, it's going to need to be evaluated and will probably need to be modified.
Great, yeah, and related to that, with duct work, what are the typical duct sizes that are used for ducted split systems? Are there, specific guidances that are followed there? Or does it vary?
It's gonna vary. I mean, it depends on how big the unit is, right? So the larger the terminal unit, the larger the outlet of that. So, it could be, circular duct work, it could be, a rectangular duct that goes into a trunk line. So it is going to vary a little bit in terms of the capacity one, and then the manufacturer and how they discharge that air. But, typically, for most spaces, you're talking, 5 to 6 inch ducts for most conventional rooms. In some of the higher performance buildings, you may be able to get away with 4-inch ducts. It all depends on the load of the space. So that's really going to dictate how much air needs to get into the space in order to adequately heat or cool it.
Great, thanks. And another one here. One person indicates they've been told that their 10-year-old heat pumps are no longer level. However, that re-leveling them at this point could adversely affect their performance. Do you have any comments on that?
No, I mean, that shouldn't affect the performance, re-leveling them. I mean, typically what they would do with those older heat pumps is there's a process of pumping down the refrigerant. So you would pretty much store, the outdoor unit is usually large enough to be able to store all the refrigerant in the system inside of it, inside of those coils. So they would typically just pump that unit down, store all the refrigerant in the outdoor unit, cut the line set, re-level it, remake the connection, again, follow the evacuation, charging, all that stuff process. But that shouldn't adversely affect the operation of the heat pump by trying to re-level it. But that's something that I would advocate for, just because, again, you may have run the risk of not getting proper lubrication to the compressor, because if the unit is off a little bit, the oil level is going to be a little bit off inside the compressor itself.
Yeah, that's really helpful. Thanks, Adam. Kind of related that you mentioned the refrigerant. One person's asked around refrigerant leaks. Is there concern for that being, toxic in a household if there is a leak or outside a leak, and how to address that?
Yeah, I mean, so when you look at refrigerants, I mean, one of the things that, I mean, it's changing a little bit, but one of the things that was governing them is that they have to be non-toxic and non-flammable to go into residential applications. So, there's really is no risk of toxicity. It's more of a risk of volume. And for a single family home, it'll be okay for the most part, because you have a lot of interior volume compared to the amount of refrigerant inside of a typical unit. But in larger multifamily complexes where you have small apartments and a lot of refrigerant, pounds and pounds and pounds of refrigerant, tens of pounds, if there is a leak in a space, it is heavier than air, so it could displace the air in that section of room. It hasn't really happened, but there typically isn't much of a concern for refrigerants leaking into the space, because they dissipate pretty quickly, and there's a lot of air in there. It's just going to cause a capacity issue.
Great,
so
thanks.
What you're going to notice is, that the capacity, you're not able to heat or cool the space, and the units are going to be running for long periods of time, or you're going to see the telltale, sort of ice buildup on the outdoor unit during summer operation.
Great, yeah. And then I think this might be our last question, but
Sure.
Can you just speak a little bit about when ERVs are recommended in terms of heat pump systems, and how those performances can work together?
Yeah, no, I mean, ERVs, I mean, it's a great option, especially when you look at your sizing, right? So when we're sizing for, our heat pump system, we have a load that is going to be through, convection and conduction, all the, the losses through the structure and all of that. And then we have losses that are going to be associated with ventilation, right? Because you need to remove air from the space, and then we need to bring air back in. And if we don't condition that air that we bring back in, that just becomes an added load on our equipment. So if we incorporate an ERV or an HRV into our system design, that is going to help reduce that load, so that the unit is going to deal with all the transmission losses through the structure, and the ventilation load is, in a large part, can be sort of satisfied through the ERV or the HRV as it's operating. So it's a great combination when you're designing a new building or a new home. It's something that's great to put in because one, you're getting good ventilation, but two, you're reducing that ventilation load on your systems.
Great, and there's one quick question I want to get to before we conclude here. Can you install heat pump compressors in an unconditioned attic as opposed to the outdoors?
So I have seen heat pumps installed in certain areas. So I mean, the only thing that is going to be, I mean, you need enough space, enough airflow, so that's going to be important to ensure that there's enough air getting into that space, all right, naturally through ridge vents and soffit vents and all that, because once you start to absorb heat or reject heat into that airstream, if there's no way for that air to change over, then the temperatures are just going to elevate or they're just going to drop. And then the capacity is going to we're going to have an issue with capacity there, because it's going to be either getting too hot or too cold in the space. So if there's enough free flow of air to get in to satisfy the flow requirements of the unit, you can do that, but it's going to, in a, two different season kind of area where we are, or 4 seasons, it's going to perform well in one, and it's going to perform, it's going to be very poor during the summertime because it's going to be very hot in that attic. So you're not going to get a good amount of performance there. It may be better in the winter because it's shielded, but most of the new units now, can perform at very low ambient. So I wouldn't be concerned with trying to absorb, waste heat from the attic space. You're probably going to have more of an issue with having adequate airflow.
That's great. Yeah, thanks, Adam. And I think, that brings us, I think, to the conclusion of today's presentation. So thanks very much. And Anna, do you want to just remind folks where they can find the recording, and if anyone's looking for CEUs for today's presentation?
Yep, so we will be posting our recording on the Connecticut Passive House website, and we'll email you all a link to that. Also, if anyone wishes to receive AIA or BPI credit, we will be sending out a survey in an email to collect all of your info. So look out for that in your inbox if you want to receive those CEUs.
Great, thank you. And thanks so much, Adam. We appreciate your expertise and time today.
Yeah, great. Thanks, everyone. I appreciate your time as well.
Thank you. Bye.
Thanks, and thanks again to the sponsors of Energize Connecticut. Yep.
Thanks. Bye.